Hey everyone! It's been a while since I made my last video, and that's because I was busy with other stuff, like making telescope mirrors. Now most things were actually quite unexciting, apart from one exception, my visit to the ZERODUR production facility of SCHOTT in Mainz, Germany a few weeks ago. The people at SCHOTT invited me to take a look at some of their manufacturing processes, an opportunity that of course I couldn't resist. I got to see how blocks of hot glass weighing over 2 tons were quickly cooled down to below the nucleation temperature. And let me tell you, the amount of heat that these release during cooling is really mind-boggling. It's enough to turn a huge production hall into a cozy infrared sauna. I also got a tour around the CNC manufacturing facilities, which can process parts up to, let's say, 6 meters in diameter with very high precision. And apart from polishing to optical specification, they basically do everything in-house. Now, of course, to make these parts to spec, you also need to be able to measure them, and to do that you can't use a simple caliper. So instead they have this rather substantial coordinate measurement machine that has an accuracy of 1.5 microns over several meters of distance. And to achieve this, the hole where the instrument is located is temperature controlled to 0.1 degrees Celsius. And that's what all these air inlets are for. All in all, the visit was pretty impressive, so I want to thank the people at SCHOTT for this opportunity. And just to be clear, this video is not in any way sponsored by SCHOTT. I just wanted to show you this. Anyway, let's not get too much distracted from the main subject of this video, which is making adaptive optics. In particular, making a deformable mirror. Now, deformable mirrors are, for example, used in large Earth-based telescopes to improve image quality. And the reason is that the image resolution of a traditional Earth-based telescope is limited by atmospheric turbulence. And turbulence is basically the flowing and mixing of air that has different temperature and humidity levels. And due to this, the atmosphere contains small but rapidly changing variations in refractive index, and this causes small disturbances in the wavefront of light when passing the atmosphere, which in turn causes unsharpness in the images recorded. And the amazing thing is that adaptive optics can correct for the effects of turbulence and recreate the original sharpness. So how does this work? Well, a commonly used method is creating an artificial star with known properties by using a beam of light from a sodium laser. And this artificial star is created in the mesosphere, which is about 90 kilometers above ground level. The mesosphere is also rich in sodium, which originates from asteroids burning up in the higher atmosphere, and the laser can excite these molecules and then force them to re-emit light at a very distinct wavelength. And this creates an artificial star that can be observed with a telescope. Now, in a traditional telescope, all optical surfaces are fixed and are manufactured to a very accurate shape, and this shape would result in a good image with no wavefront distortion being present in the light. However, if the wavefront is distorted, the light is actually ending up in the wrong place on the sensor. So to solve this problem, one of the mirrors, like for example the secondary, is replaced with one that has a variable surface shape. So this is illustrated here, where the mirror surface is on a relatively thin sheet of curved glass, and this sheet is generally only a few millimeters thick and is attached to a bunch of linear actuators. And what this mirror can do is dynamically change its surface shape such that it exactly counteracts the wavefront errors present in the incoming light. And if you do that very quickly and with high accuracy, you can keep the telescope focused regardless of turbulence. But of course we need to know what the shape of this deformable mirror must be to do this. And this is where the artificial star comes in. It can easily be isolated from the rest of the image by optical filtering at its emission wavelength. The star's image is then projected on a wavefront sensor that can measure the shape of the wavefront, which is then analyzed, and then a complex matrix calculation is done to establish the desired position of each individual actuator and change the shape of the deformable mirror surface accordingly. Now, the effects of turbulence typically occur on the millisecond timescale. So within a time frame of approximately a millisecond, you have to measure the wavefront, then calculate the desired change in surface shape to correct for the error, and then apply these corrections to the mirror surface. And for this reason, the adaptive mirror surface itself must be thin and lightweight. And that is why adaptive optics are generally not implemented in the large and heavy mirrors like the primary, because that would make fast changes in shape very difficult. Here are two examples of adaptive mirrors that are actually used in telescopes. This is the adaptive secondary that was made by TNO, the Netherlands, for the IRTF, an infrared telescope of the University of Hawaii. Now, fun fact, I actually made a small contribution to this mirror by cutting and polishing the face sheet. It was then sent to TNO, where it received an aspherical shape correction and was then coated. And these blue cylinders contain the actuators that can pull and push the surface into the desired shape. Here's another example from the multiple mirror telescope in Arizona. This one has 336 actuators to press the surface into the correct shape. And maybe now you wonder, why so many? Well, the effects of turbulence not only occur on a typical time scale of milliseconds, but also on a typical dimensional scale, described by the Fried parameter, which refers to the maximum aperture size that leads to an undistorted image. And the typical value for the Fried parameter is around 100 to 200 millimeters for normal atmospheric conditions, maybe 300 to 400 for a very quiet atmosphere. So if you have a small telescope, say smaller than the typical Fried value, the turbulence mainly changes the angle slightly at which we observe an object. However, with very large telescopes, the total wavefront error over the telescope aperture is the result of multiple turbulent cells, and this in turn results in a wavefront that contains a fairly complex deformation within the total aperture. So to correct for this, you need sub-aperture or local corrections of the wavefront in the optic. Now, the current MMT's primary has a diameter of 6.5 meters, which explains why you need so many actuators to correct for wavefront errors. In this image, I sort of summarized what kind of aberrations you can expect based on telescope aperture. So if you have a telescope with a diameter that is smaller than the Fried parameter, you basically only have to correct for small angular variations. And this can be done by the introduction of what we call prismatic corrections, like tip and tilt. Basically, this is a form of fast image stabilization. Now, if we look at larger diameter telescopes, the total wavefront error can only be corrected by a combination of more complex aberration types. So the larger the telescope aperture, the more complex the corrections need to be to, let's say, undistort the wavefront. Okay, let's do something practical with this concept. Now you can imagine that I'm not going to make a fancy multi-million-dollar adaptive optical system with all the electronics. Instead, I want to focus on making the deformable mirror part. So just the face sheet with some actuation, and not with hundreds of them, but a very limited number. Let's first discuss the design I had in mind. I want to start out with a relatively rigid support plate as the mechanical basis. Here on the surface I indicated the position of a total of 25 actuators, which will be glued to this back plate. If we zoom in on an individual actuator, we see that it consists of a central pillar made of a flexible material, like for example a silicon rubber. The pillar itself is inside a small reel or bobbin that consists of two parts to simplify manufacturing, and this can be used to wind a copper coil on, so it will basically hold the electromagnet. And we can run a variable current through the coil to attract or repel the magnet that is glued on top of the silicon pillar. So that's basically the whole actuator construction. It's pretty simple. Now, the only thing still missing here is the face sheet, which represents the deformable mirror. And this is just a sheet of glass glued to the magnets. Now, since we're not going to put this thing into a telescope and it's just a proof of principle, we can settle for a flat piece of glass for now. And this also makes manufacture and measuring deformations a lot easier than when using a curved surface. Here's a cross-section of a finished actuator. Depending on the polarity and the current through the coil, a variable attractive or repulsive force can be exerted on the magnet and therefore on the face sheet. And so, in theory, we have a very simple and direct way to deform the shape of the face sheet surface. Now, of course, the extent of the deformation would be very dependent on the thickness of the face sheet and the forces that can be exerted on the magnets. And at this point, we do not have a good idea about what kind of forces will act on the face sheet and what this means for the thickness of the face sheet. It probably has to be quite thin because the actuators are small and can likely not exert large forces anyway. This means that, for example, a 4mm Roback sheet will be way too thick because you need several newtons of force to change the shape significantly. So what I'll do is I'll start out with a phase sheet cut from an old quartz photomask, which is 2.3mm thick and which is pretty flexible on the micron scale. But if that's not sufficiently thin enough, I've got another option. Maybe you remember that at the end of the last video I had received a mystery package from Japan. And this package was very kindly sent to me by the people at Nippon Electric Glass Company. Now don't be fooled by the dimension of this package. It just contains two relatively small glass plates with thicknesses of only 1.6 and 1.3mm respectively. But of course this is no ordinary glass. This is a zero expansion glass ceramic that comes in thin sheets and which is appropriately named Zero. Now if you look at the thermal expansion of this material as a function of temperature, you can see that it hardly contracts or expands. Even over a temperature range of -40 to +80 degrees Celsius, it expands less than 2 microns per meter of length, which translates to 0.016 ppm per degree Celsius, which is pretty impressive. Now, it was not my initial intention to use this material to make a phase sheet from, but as hopefully will become clear, there might be some advantages to using zero thermal expansion in the current application because of heat development. Anyway, these sheets are certainly quite a bit more flexible because they are so thin. Unfortunately, they're also not very flat, which might be a bit of a problem. So let's just start with using the quartz plate, and if that doesn't work, we'll try these, because making these flat will be quite a challenge. Okay, so let's do this. So this is the complete device. Now, if I connect the central 9 actuated coils to a high frequency square wave, I think it's a little over 2 kHz, you can clearly hear this annoying tone. So the phase sheet is moving up and down with this frequency and starts acting like a speaker cone. So it seems that in principle we can move the phase sheet up and down pretty fast. Now let me quickly discuss the choice for the copper wire thickness in the actuated coils, because this is actually kind of an interesting aspect. You probably know that a current running through a wire creates a magnetic field, and if you wind this into a coil, the magnetic field in the coil is proportional to both the number of turns and the current running through the wire. Now, as for the magnetic attraction or magneto-motive force on the magnet, this property is not proportional to the magnetic field itself, but to the gradient in the magnetic field. That said, if you have a field with a constant shape with a magnet held in a more or less static position, it is to be expected that the force acting on the magnet will be proportional to the number of turns times the current running through the wire. Now, it's tempting to think that because of this we want a lot of turns, because with the same current we can exert a higher force on the magnet. And even though this is in principle true, we're actually not interested in the current running through the coil, we're interested in the amount of power dissipated by the coil, because that determines how hot these will get when we run a specific current through them. For a resistive wire, the power dissipated is the current squared times the resistance. So what is the optimum value for the number of turns given that we have a limited volume available in the bobbin and we have a maximum value for the dissipated power that is allowed? Well, the answer is kind of surprising. Let's start out from the assumption that the magneto-motive force is proportional to the number of turns times the current. The number of turns that we can create in the coil is the volume of the coil, Vc, divided by the cross-section area of the wire, Aw, times the mean length of a single turn, Lm. It's pretty straightforward. Basically, this is the total coil volume available divided by the mean volume of a single wire turn. Now, the current and the wire resistance are what makes a coil dissipate power, and if we assume a certain maximum power dissipation level, the corresponding current is equal to the square root of this maximum power divided by the internal resistance of the coil. On the other hand, the resistance of the total wire can be written as the conductivity, in this case of copper, times the volume of the coil divided by the wire cross-section area squared. Now, I'm not going to write this all out, but if you combine these, you can arrive at a formula that shows how the force on the magnet is proportional to the length of a single turn, the power dissipated, the total coil volume and the resistivity of the conductor. And what is surprising here is that the number of turns, N, is nowhere to be found in this formula. It's just about coil dimensions, conductivity and the amount of power that you're dissipating. So in essence, it doesn't matter whether you use 6 or 20 or 80 turns. When power dissipation is the parameter you steer on, any of these numbers will result in approximately the same force on the magnet at a set power dissipation level. Of course, there are a few practical details here. A very thin wire might have a relatively thick isolator mantle, so that would actually not help because it would reduce the amount of copper you can get into the coil volume and increase the resistance. Also, it would reduce the thermal conductivity of the coil itself, but in the end, a choice for a particular wire thickness is about which is most appropriate for your driver. Apart from that, it doesn't really matter. Anyway, with the choice of the number of turns and the wire diameter being more or less irrelevant, I did a few tests and I chose the 0.22mm wire mainly because it allowed me to make coils that had a DC resistance of 1 ohm, which is convenient. So to run it at 1 amp you need 1 volt and it produces 1 watt of heat. And it turns out that the force that is generated is around 0.1 newton with the 6mm diameter magnets that I used. I must admit that this is much less than I expected, but let's try to work with it. Okay, let's first try to measure the faceplate as is in the interferometer without any currents running through the coils. And for this measurement we don't want the top surface to have a highly reflective mirror coating because the interferometer compares the surface with a flat that has 4% reflection, the same as the uncoated glass interface. So here you see the setup with the deformable mirror, the interferometer with the reference flat on this side. I've opened up the interferometer to expose the camera and the camera is connected to a laptop PC. Those of you that are familiar with DFT Fringe will have noticed that I'm using a different type of software here. So while I was considering making this video, I was contacted by Jaco Verster, a researcher from South Africa who was developing near real-time interferometry software. And he asked me if I was interested in testing it and give some feedback, which of course I was because I thought this project would be the perfect test case for that. The software is called Wavefront Pro, and you will find more information in the description of this video. The reason for using it here is that it performs a wavefront measurement from an interferogram every second or so. And this feature allows for measuring wavefront shapes almost in real time. This allows us to immediately see how much the phase sheet deforms when we activate the actuators. Now, I think it's good to point out that Wavefront Pro, since it has been developed recently, does not have the same functionality as DFT Fringe. It's not suited for evaluating aspherics, and it does not calculate wavefronts with the same level of detail. But its power lies not in the number of features, but in the interactivity. So if you want to tweak your optical assembly, you can do that because you see the result of your actions on the screen immediately. Now, one of the features I really like is that you can use any wavefront or average of wavefronts as the reference or 0 point for your measurements. And this allows you to observe very small changes in the shape of the wavefront. I don't want to discuss the software in too much detail, but just take you through an example of the main screen, which contains the camera image with the interferogram, the intensity profile of your fringes to avoid that you're overexposing the image, a contour plot of the wavefront, a plot containing two cross sections taken from the contour plot, and a 3D representation of the wavefront. To the very right, a list of Zernike polynomials and their contributions, and these can be switched on and off to either include or exclude specific aberrations in the analysis. To set up the interferogram, you can open up a detail screen in which you can choose which area to evaluate, and you can set spatial filtering, and that's it. Once you've set this correctly, we can start measuring. Okay, so let me just show you a few results. At some points I will freeze the video so we can take a closer look at some details. Now, this is the shape of the phase sheet without actuation. The measurement includes the tilt with respect to the reference, but as you can observe from the fringes and the wavefront evaluation, it's not flat but about 6 lambda concave. Now let's use this shape as the reference value and then subtract it from all the upcoming measurements. In a moment I will add a little schematic in the left bottom corner that shows which actuators are active. Gray actuators are inactive, a red actuator is pushing the surface up, and a blue actuator is pulling the surface down. So here you see what we observe when we push on one side and we pull on the other. We can tilt the mirror surface by about 26 lambda wavefront at 1 amp per actuator, which is equivalent to about 8.2 microns of surface tilt. Here you see how we can deform the surface by actuating the center 9 actuators, and this results in almost 10 lambda peak to value deformation of the surface.
Let's do that one more time so you can see it was not a fluke.
Here I've created astigmatism by selectively pulling on a few actuators at the edge. As you can see, the latter deformations are pretty small, few lambda, and I can use the center actuator to press up, which changes the overall shape of the astigmatism a bit. Okay, so this all seems to work, but what doesn't work with this sheet thickness is that you cannot clearly distinguish the effects of actuators that are next to each other. Say that, for example, we pull down the center actuator while pushing up the middle ring at the same time, then with the current device it's very hard to spot the effect that the center actuator has. It is basically just counteracting the effect of the others. So what this means is that the phase sheet is not flexible enough to create higher order deformations, which in turn means that we should go to thinner phase sheets like the zero plate material, which is only 1.3 mm thick. The problem with this sheet is that it's currently not very flat, so we need to solve this issue first. So here we got our new and improved deformable mirror. One thing I didn't show is that I had to take off this face sheet again to spray black paint on the back side. This is intended to remove the double reflection originating from the back side of the face sheet, which in this case would screw up the interferograms. So here are a few tests on the new sheet. This is the shape of the face sheet without any actuation. Again, not very flat, but about 9 lambda convex, which is kind of embarrassing. Fortunately, we can subtract this shape from our measurements, so now it seems nice and flat. Here I'm pulling on the center 9 actuators at 1 amp, making the surface 22 lambda concave. Here you see astigmatism created with 8 actuators, amounting to 6 lambda peak to valley. And this example shows tilt of over 100 lambda using the actuators in a different configuration. So for now it seems that the deformations are larger at the same current, but the main question and the reason why we did all this extra work is, can we see the effect of a single actuator here? Now the answer is yes. If we pull on the inner ring of 8 actuators and then start pushing with the center actuator, we can indeed create a shape that represents the action of these forces. So what you observe is really dependent on how hard you push on the center actuator. Here I'm slowly increasing the force on the center actuator. And what you see is that the very center comes up and the surface as a whole becomes more aspherical. We can also exert exactly the opposite forces and create a deformation that looks a bit like a donut. So all this means that we can create shapes that in principle can correct for higher order aberrations. Now I realize this is still a long way from making an actual adaptive optical system, but I think it's pretty cool that it can be made with a simple actuation method and a very limited number of actuators. There's still one thing I need to point out, and that is the heat development by the power dissipation in the coils. So after I've stopped the actuation of the center 9 coils here, you observe that a bump has formed in the center of the sheet. And the reason is that by activating these, we've also heated them up a bit. Now this heat development is not a problem for our face sheet or backplate, which are both made from near zero expansion materials. Now it's actually caused by the heat getting transferred to the silicon pillars, which have a relatively high coefficient of thermal expansion. So it's the expansion of the pillars that is pressing the face sheet upwards. By the way, you can also observe the heating up with a thermal camera. It takes several seconds for the heat to also reach the top of the face sheet, but the effect is very clear. Now obviously this is a major design flaw. Any pillars supporting the face sheet, especially when they have a high thermal expansion, should never be close to where the heat is generated. But in hindsight, there are a lot of other things I would have done differently. For example, make a dedicated PCB with coils integrated instead of this wire mess. A PCB that can also effectively transport heat to a conducting backplate to keep it away from the face sheet and its supports. Or maybe even better, abandon the whole idea of magnets and coils altogether and use small piezo actuators instead. Ah well, you live, you learn. Anyway, hope you enjoyed this video. If you have any suggestions for improvement of the device, please let me know in the comments. I feel that this might not be the end of this project.